Hello, AP Statistics students. Um, I unfortunately am going to be out today and possibly a couple of more days, so I got some videos for you here. Today we are taking a look at a difference of two proportions. What if I have two samples and I want to compare them? All right. And we are still looking at their sampling distributions, but now we've got two populations, two different proportions that we are looking at. You're still going to have some homework on sapling like usual. With the short week, it's going to be due on Thursday, and then we'll have our quiz on Thursday, whether or not I am there. All right, so that is what's happening. All right, the difference of two proportions. What if we take two samples from two populations and we want to compare them? Well, we've actually sort of done this before when we combined random variables. That's why we did this way back then. Is if you have two random variables and you combine them, what happens to the shape? Nothing. Nothing happens to the shape. A normal distribution plus or minus a normal distribution gives you another, shocker, normal distribution. All right, you can add a normal distribution plus a normal distribution and you get a normal distribution. All right, what happens to the center? All right, well, you can also simply add or subtract the centers, the mean, any location, whether at minimum, maximum, Q1, Q3, you can add or subtract the middles. All right, now what happens to the spread if we combine two normal distributions? Well, if you, the spread, that was the tricky one, you cannot add or subtract the standard deviation. All right, you cannot add the standard deviations. But you can add the variances. All right, you can add the variances. So remember, this is where the standard deviations of the first variable, the standard deviation of the second variable, we can't add those. So we have to square them. And then we can add them together. But then we got to get rid of the squares, so we square root to go back towards the standard deviation. So if you want the standard deviation of the first variable combined, either adding or subtracting the second variable, that is equal to the square root of sigma 1 squared plus sigma 2 squared. All right, hopefully that rings a bell. We did that before break. All right, so what does this actually look like? So here's a scenario that actually puts this into practice. So suppose there are two very large high schools, Edison and Sunnyside. At Edison, we know that 70% of the students did their homework over the weekend. You lucky, I don't even give you homework on the weekends. All right, at Sunnyside, only 50% of the students did their homework over the weekend. All right, so we know those are our parameters. All right, that's what we know is true for the populations. But now I'm going to take a random sample of 100 students at Edison and record their proportion of students who did their homework, P1 hat. Mr. Schneider, he's the stats teacher at Sunnyside, takes an SRS of 200 and records the proportion, P hat 2, that did their homework over at Sunnyside. So to compare our results, we are going to take P1 hat minus P2 hat and make a sampling distribution. What could they look like? All right, so first off, shape. Let's just talk about Edison here for a second. What does Edison's sampling distribution look like? Well, we know the parameter was 70%. So we know the sampling distribution for Edison will be centered around 70%. But of course, I may not get a sample exactly like the proportion for the parameter. Sampling variability, right? But we know this is going to be normal. Ooh, I got to check that though, don't I? Yes, I do. All right, so here's my sampling distribution of all the p-hats. So the sample I get is going to be somewhere, maybe it'll be over here. Maybe my sample will be over here. Maybe my sample will be up here. Maybe my sample will be over here. I don't know where my sample will be, but it will be somewhere in that normal distribution. Let's make sure it's normal. N times P and N times Q. So I'm taking a sample of 100, right? Yeah. So 100 times 0.70 is 70. 100 times 0.30 is 30. And those are both greater than or equal to 10. So yes, this is going to be a normal-ish, normal sampling distribution. All right, the center, we do know that the average of all the p-hats will be equal to 70. All right, that's the center. The spread, so the standard deviation of all the p1 hats is going to be equal to the square root of 0.70 times 0.30 divided by 100. Let's see here, there. Square root of 0.70 times 0.30 divided by 100 gives me 0.458. 0.0458 is my standard deviation. Again, I should call out the 10% condition, and we can do this because 100 is less than 10% of Edison's population. All right. All right, now let's do the same thing for Sunnyside. Does theirs also work? All right, so Sunnyside, yes, all of that's P1 hats, all the P2 hats. What do those look like? Well, he's doing 200, but their parameter was only 50%, right? Yeah, 50%. So 200 times 0.50 is 100. And yes, technically you do need to do it again, because that's N times P. Here is N times Q. Yes, it's the same, but you got to do it both times. Which is greater than or equal to 10, which is greater than or equal to 10. So we know the shape of their sampling distribution is also normal. Yay! All right. We know their center is at their parameter, which is 50. The mean of all of Sunnyside's p-hats is equal to their parameter. And the spread is equal to the square root of 50 times 50 divided by 200. So what is their standard deviation? The square root of 0.50 times 0.50 divided by 200. 0.035. I'll do one more decimal. Why not? 4-ish? All right, but now I want to take these two sampling distributions and I want to combine them. What would they look like together? All right, if we combine these, what could it look like if I took a sample from one, a sample from the other, and then subtracted them? All right, dun, 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 dun. And so we are going to take P1 hat minus P2 hat. What could it look like if I took a sample from one population, a sample from the other population, and subtracted their proportions? And then did that over and over and over and over again until I had a whole bunch of proportions representing a whole bunch of samples. Well, if I take a normal and I subtract a normal, thankfully, I get a normal. Where is it going to be centered at? Well, it's going to be centered at the true proportion. The true proportion, P1 minus P2, is just 0.70 minus 0.50. So the center will be at 20. Usually, if I take a sample from Edison and a sample from Sunnyside and I subtract them, usually I should get around 20%. But sample variability means sometimes the Edison sample will be a bit lower. Sometimes the Sunnyside sample might be a little bit higher. And so when I subtract them, you might get different, well, you will get different numbers than 20, but they're going to be centered at 20. Now, the variables get kind of weird here. So this is the average of all the P1 hats minus the P2 hats. Yeah, that's all subscript. All right, sorry. Is 0.20. All right, the hard part here is the standard deviation. What is the standard deviation of P1 hat minus P2 hat? All right, now we can't simply add or subtract the standard deviations. We always add the variances. Okay, we always add the variances. So I'm going to take my first number, 0.0458. I have to square it to turn it into a variance, plus 0.0354, square it to turn it into a variance. Now I'm allowed to add them. And yes, you always add them even though we are subtracting, even though we're finding the difference in proportions. When you combine two random variables, the randomness of both variables always makes things more spread out. Okay, so you always add the spreads, always add the variances. But of course, I don't want the variance, so I square root it to turn it back into a standard deviation. All right, so there's my formula there. So I have sigma of P1 hat minus P2 hat is now equal to, I got to type all of that in. All right, so we got the square root of 0.0458 squared plus 0.0354 squared. And I get 0.05, let's go 0.058. So you see that is bigger than the other two standard deviations. So the standard deviation did go up. All right, it is bigger than this one. It is bigger than that one. But it is not the sum. You don't add them up. Add the variances, square root it. All right, well, now I have a normal distribution that describes what it should look like if I take those two samples and subtract them. What could the result look like? And now that I have a normal distribution, I can find some probabilities. So what is the probability that P1 hat minus P2 hat is positive? P1 hat minus P2 hat. Positive means greater than 0. All right, what does that mean? Well, if P1 hat is bigger, that means more students at Edison turned in their homework at Sunnyside. What are the chances that my Edison sample is actually bigger than the Sunnyside one? Well, it's a normal distribution. I can simply do normal CDF. I know the mean is 0.20. I know the standard deviation is 0.0, was it 58? What was it again? Yeah, 0.58. Lower, all right, greater than 0. So my lower is 0. Yeah, I should write lower. And my upper is going to be infinity. All right, if you want a picture, here's my normal model. Careful, 0 is not in the middle. 0.20 is in the middle, right? We expect 0.20. But what are the chances we're at least bigger than 0? So 0 is over here. So I'm finding this area right there. All right, let's do that. All right, second distribution, normal, CDF, lower, 0, upper, 0.20 is my mean. My standard deviation is 0.058. There is a 99.9% chance. All right, a 99.9% chance that my Edison sample is bigger than my Sunnyside sample. Okay? All right, so now this is another question. Suppose Mr. Bolt and Mr. Snyder compare their samples, and they get P1 hat minus P2 hat to be negative. This means in our sample, a higher proportion of Sunnyside students did their homework compared to Edison in our sample. What should we conclude then if that is actually the case? Well, there's a 99.9% chance of this not happening, assuming this is true right here, and assuming all of this is true. If, in fact, the true proportion for Edison is 70 and the true proportion for Sunnyside is 50, there's a 99% chance that the Edison will be bigger than the Sunnyside. But if we get Sunnyside being bigger than Edison, whoa, that gives us a lot of evidence that our original assumptions are false. All right, so there was only a 1%, or there was only a 0.1% chance of this happening because of sample variability with our original assumptions. This gives us a lot of evidence that those original assumptions are false. All right? That whatever the difference between Edison and Sunnyside are, it's not 0.20. And, all right, P1, how can I get the hat? Oh, I'm just going to write hat. I know that P1 minus P2, I don't want the hats, is not 0.20 and must be less. All right, those original assumptions must be false because there is only a 0.1% chance of this happening because of sample variability. So I'm going to bet that it wasn't sample variability, that it was something else. The assumptions are wrong. Not necessarily somebody's lying to us, but that it's different. All right, everybody. Hopefully that makes some sense. I got a Desmos for you all to practice now. It should already be there waiting for you. Try that out, and hopefully a difference of proportions is making some sense.